When you pluck a guitar string, how does it know what note to play? The answer, it doesn't. The wave does. So this video is about standing waves. First of all, what's a standing wave? A standing wave is formed when two waves of the same frequency and amplitude travel in the opposite direction and interfere. So interference, like we talked about in the last video. What does that look like? When would that happen? It typically happens when a wave reflects back on itself and it's fixed on both ends. It means both ends are at a fixed point and it will invert and bounce off when it collides on one side. So imagine you have a straight rope and it's attached to the wall. You decide to start moving it up and down at a constant rhythm. Your rope also starts to moving up and down. And let me draw this wall again. It travels like this. Keep flicking it, moves up and down. Yep, it's oscillating like this. Try and imagine what's going on here. It's moving up and down. Move your hand straight up and down. Now, let's say you're moving at this constant rhythm. Instead of traveling forward like a normal pulse does along a rope, what happens is it appears to stand still. The same points oscillate up and down at the same distances. And there's fixed points that aren't moving at all. These fixed points being here, it's not moving, and here, these are called nodes. And the spots that are moving are antinodes. So nodes are permanently zero, no oscillation. Antinodes are the point of maximum oscillation. So when you shake it at the right frequency, the reflected waves when it hits the wall and the incoming waves from your hand moving up and down align. So the energy doesn't escape and it becomes a standing wave. It can have as many nodes as you want, it just has to have nodes at the ends. Now I have to tell you about natural frequencies and resonance. A string can only support specific patterns. And these patterns are whole number fractions of the wave. These are its natural or resonant frequencies. I'm going to derive some important stuff. If you don't care, skip it, and the formula I'm deriving is on the free cheat sheet in the description. A standing wave picks exactly n amount half wavelengths inside a string of length L. Try and follow along. It's going to make sense as we piece it together. This means that the length of the string is equal to n times the length of n amount divided by 2. That means the number n wavelength is equal to 2 length over n. And this formula is important. What does this mean? Imagine our rope again. We love our rope. It's a wave traveling along like that. This here is the wavelength, right? The distance between the peaks. This here is the total length of the string. And n is equal to 1, 2, 3, up and up and up. N is whatever we want. So, if n equals 1, let's try that formula. It's equal to 2 times length. That means half a wave fits on this length. Let's say n equals 2. That means it's 2L over 2, which is L. That means the wavelength is equal to the length of the string, so one full wave fits. If n equals 3, what happens? Well, it would be 2L over 3. So if it's a string that's fixed on both ends, only certain amount of wavelengths can fit on this length of string. They must form nodes at both ends. Remember what nodes are? It's points where there's no oscillation happening. By the way, this is on the pre-cheat sheet in the description so that you don't have to memorize this formula. Time for the next formula, which is related to frequency. So the frequency formula is V over wavelength. This is taken from the standard wave velocity formula. That means the frequency and amount is equal to the velocity divided by an n amount of wavelengths. And with our formula that we just found, 2 length over n, we can sub in this value for wavelength. And our new formula is F equals velocity over 2 length over n. We'll go one step further. NV over 2L. That's our new formula for frequency. And this is also on the free cheat sheet in the description. Now, n equals 1 is the fundamental frequency. You can think of this as like the default. And then n equals 2, 3, 4, and so on. These are the harmonies and overtones. So let's recap this. In English, the higher the harmonic number n, the higher the frequency linearly. They're directly tied. So you can fit more bumps in the same string because it oscillates faster, even if they are of the same length. Here's an example problem. A guitar string is 0.65 meters long. And this guitar string has a mass of 5.2 grams. What tension of this string must it be tuned in for its fundamental frequency to be 110 hertz, which is the note A? And we'll also calculate the next three harmonies. So our goal, calculate tension based on these things: wave speed, frequency, and string length, and then use the standing wave equation for harmonies. The free cheat sheet in the description is going to help a lot here. Every formula for this topic is on there. So have a look. Step 1, we're going to convert our mass from grams to kilograms. 0.005 to kilograms. That's how much the string weighs. 2, we're going to find the linear density, which if you remember was this value. It's the mass per unit of length. So it's the density of our line. So it's mass over length, which is this value, 0.0052, over the length, 0.65. This is roughly 8 times 10 to the power of negative 3 kilograms per meter of length. So I'll quickly set that aside because that's a useful value. Step 3, we're going to use the wavelengths of the fundamental frequency. So for n equals 1, the formula, wavelength of 1 equals 2 times length. 2 times 0.65, giving us 1.30 meters. Nice formula. We're going to rapid fire this. So wavelength for frequency 1 is 1.30 meters. Next, the wave speed, which is given with this formula. Formulas. Frequency is 110 hertz. The wavelength we just found, 1.3. It's 143 meters per second. That's the wave speed done. Final step, we're going to solve for tension. We're going to select the formula that links everything that we have, so all these frequencies, wavelengths, with what we need, which is tension. There's a perfect formula for this. It's velocity equals square root the tension divided by the linear density. We can use our excellent math skills here to rearrange for tension. Tension equals that symbol of density times velocity squared. And rearranging fast helps you a lot. So I recommend you try and find a way to become not just good at it, but excellent. A lot of people struggle with physics not because physics is hard, but because they haven't trained the right math skills in the right topics, and they don't have structure in their solving. Anyway, sub in our values. This, and you get the tension, roughly 163.3 newtons. That's the tension in this string. I also said that we're going to solve the next three harmonies of our guitar string. How do we do that? The frequency at n is equal to n f1. And if you're wondering where this formula came from, yes, I know it's a lot of formulas. It's because if you remember the frequency formula that we derived earlier, say n equals 1, well, it becomes v over 2l. And guess what? If you split up this fraction, you can write it like this, n times v over 2l. Wow, look at that. They're the same, so we can sub in f1. So fn is equal to n times the frequency when n equals 1. That's where this formula comes from. Now, we can simply find the frequencies. At 2, which is the harmony up, it's 220 hertz. At f3, 330, and at f4, it's 440. So you can see that harmonies are whole number multiples of the base frequency, which was 110. This makes studying 10 times easier. Go download the free cheat sheet in the description, and I'll include a free surprise worksheet from my premium study kit to help you understand this topic.